Welcome to third class of theory of plates. So we have already covered reviews of basic equation of theory of elasticity, energy principles, and today we are going to cover that some basic assumptions and classification of various plate theories. So before going to the main course, I would like to tell you that Mary Sophie Germain, she was the first mathematician, or she developed plate theory, and this was her equation of motion. So it is a very interesting story. I have also written that some part of it which is given on a Wikipedia, that there was a competition in the Academy of Polish, then they asked that to give the mathematical theory of vibration of an elastic surface and to compare the theory to the experimental evidence. So during the competition, this topic was assigned and asked that whosoever will give the equation of motion, and later on that theory should predict the experimental results. So the importance of is that you know that Euler-Lagrange, that famous mathematicians, commented that the solution to the problem would require the invention of a new branch of analysis. So then the Poisson's ratio, which we call the scientist, the researcher Poisson's, was elected to the Academy, thus becoming a judge instead of a contestant and leaving the Germany as the only entrant to the competitions. And she developed that first theory of plate, but there was that time calculation of variation was not evolved properly, it was in the initial stage, so there was some discrepancy. So this theory could not give accurate results to the experiments, validations. So later on Kirchhoff's did some correction and developed the plate theory. So these days we used to say that Kirchhoff's plate theory or Kirchhoff's assumptions, that sometimes we do not call classical plate theory, we said Kirchhoff's plate theory. So the name that Kirchhoff's did give the plate theory first time, but before that this basic equations was given by Mary Sophie Germain. This is very interesting story. Sometimes in area that it was a area of a mathematics, that mathematicians, the researchers who are a world level mathematicians, they were in this field, in the development of the theoretical analysis for a plate or a beam. You see that Euler-Bernoulli beam, Euler was a mathematician, so he developed a beam theory. Then the Kirchhoff's, similarly the Lagrange, so both were of mathematicians, or sometimes they also did some good contribution in the physics also. So but a person, Timoshenko name is very famous name. I think everybody, whether he is an undergraduate students or the masters or the postgraduate or PhD students, have once or sometimes encountered that Professor Timoshenko's book. The books are that Theory of Elasticity or Elements of Strength of Materials, Engineering Mechanics. I would like to say that before I will comment that he is considered to be father of the modern engineering mechanics. Though the theories were developed, but they were the engineering background persons, because mathematicians developed the theories, so they were difficult to understand. So the Timoshenko was the first person who tries to simplifies or from the explaining physics point of view. So he contributed that for that engineering student or the engineering researchers can understand the theories, that theory of plates, like theory of elasticity, or in the book of engineering mechanics or element of strength of materials. So they have written in a very simplified manner, so that undergraduate students, postgraduate students who have not very strong background in mathematics can understand this concept, and afterwards so engineers like us can understand this theory and can contribute to the development of the theories of plate addition. So I would like to also emphasize on that one can develop the theory number of ways, like using the complex theory analysis method, or using the simple mathematics, or using the differential equation of motions, or using the variational calculus. So there are number of ways to present the equation of motion or to drive the governing equation of motion. So, for engineers or the researchers who works in that engineering mechanics field, so they love to work in that simplified version of that theories, so that it can be easily understood. And then I talk about that in the last lecture also I talked about a beam analysis. So, this is, you can treat as a beam, this is a simple rule, or you take the steel rule. You know that property of the steel, simple tool steel properties, what is the E, what is the mu, and clamped at one bench and try to deflect it and measure that, how much it is going or how much force you are applying there. So, whether whatever your analysis or in your undergraduate courses are standard formulas are given for that, you can verify at your home, at your hostels. So, these are not very difficult concepts. Similarly, I would like to tell that, see, this is a water bottle. If you make, this is a thin, so you can analyze this water bottle as a cylindrical shell with internal pressure, whatever the water is having, and outer is a atmospheric pressure. So, you put on the table on a rest, so this edge on the simply supported edge, other surfaces are free. So, whatever the pressure is should not burst. So, one more thing I would like to tell you, you take any water bottle and you feel that there is some roughness, zigzag portion is there. If it is made just plain, what will happen? That this water bottle is very thin, it cannot take that much of pressure. If you make some wrinkles kind of thing, or sometimes you see on the rooftop in a hilly area or in a some where it is like rainy zones, so you will find corrugated sheets, those types of sheets. So, these takes more strength compared to just a plain sheet. Similarly, in these bottles, this pattern is created, corrugated pattern, so that the same thickness it can bear more pressure or it has more strength. So, now I am going to our main topic. So, in the last class, we have formulate a principle of virtual displacement, in which this portion is your work done, internal work done, and this portion is related to your external work done. Similarly, I have stated the Hamilton principle, in which, because the virtual displacement principle cannot be used for a dynamic case. So, if you are interested to analyze a body under the dynamic case, under the time dependent analysis, then we have to use the Hamilton principle, where this portion is the contribution due to the kinetic energy, contribution due to the internal work done, and contribution due to the external work done. So, I would like to do slight correction here, it should be plus, not the minus, because already it is minus. If you put it as minus, so internal work done will get minus sign, external work done will get plus sign. So, most of the time during first course of solid mechanics, we used to teach a concept of plane stress. This is very much required, because it is simplified version. Most of the time thickness of the body is not very high compared to the length and width. Then we can apply this assumption of the plane stress. So, 90% engineering application, this concept or this assumption holds good. So, before proceeding to the main theory, I would like to explain what is the concept of plane strain. That for some engineering problems, state of stress for a thin body or a structure is required, in which dimensions along the thickness direction is very small compared to the length and width of the body. If you encounter a basic fundamental structural element in which length and width are comparable, but thickness is very small, it means you can analyze or you can find out state of stress of that body using the plane stress assumption. For such problems, the stresses in the z directions become very small. There is also a physical concept behind that. Since thickness is very small, it cannot resist, so it cannot take the too much stress. So, stresses in the thickness direction are neglected, and it is assumed that body in two dimensional in a state of plane stress. So, for that case, if you say this statement about the plane stress is given in a book of theory of plates by K. Chandrasekhar. So, you have a body, say x and y, and out of the plate there is a z thickness which is small. So, for that case, stress along z direction sigma zz, tau yz and tau zx will be 0. Most of the time students get confused here. Let us say a system like this, but I have assigned this axis is x and this axis is y and this axis is z. So, you see that along y direction thickness is small compared to along x and z direction. If you assign the coordinate system like this, then along the y direction stresses will be 0. What will be that? Sigma yy, sigma, or I will say that tau yz and tau yx will be 0. So, at the time of interview or when you are going to develop a theory on just you did not take care and you have modeled this plate like that y vertical, x and z longitudinally, in that case following components has to be 0 if you are applying a plane stress assumption, not this. So, this is when z is the thickness direction. So, plane stress application, how much? I said that length and width are comparable, but thickness is small. What do you mean by the small? This is a quantitative term, qualitative term. What is in terms of quantity? What small? Which thing you can hit small? 0.1 mm is small or 100 mm is small as per your dimension. Sometimes in civil structural application, the slab width may be 100 mm equal to 10 centimeter. You say no, it is very big, but if you see there, so this may be 10 meter long like the roof of this room or 5 meter long. So, compared to that, if it is 500 centimeter and it is 10 centimeter, then ratio is coming 50. So, that slab can be analyzed as a plane stress element. So, you see S length to thickness ratio. If this S is greater than or equal to 20, definitely we can apply the plane stress assumption, or the theory will predict the more accurate result and near to the experimental results. But if you have a S equal to let us say 4, then it is not. Like for some mechanical components, you have some according to maybe 1 mm thickness and this may be 10 centimeter and this may be 10 mm and this may be 2 mm thickness. You say that I would like to analyze or I would like to analyze this as a thin plate, or under that assumption that it cannot be possible under plane stress, because thickness length 10 mm and 2 mm. So, it is giving 5 length to thickness ratio. So, it is becoming thicker. So, this thickness can resist. So, most of the time these basic concepts are not well taken care. So, you have gone through that course of advanced elasticity, theory of elasticity and theory of latent cell and so on. But if you do not take care of this and you are going to develop without taking consideration of this aspect ratio, that whether my theory will able to predict these things or not. So, when you are going to analyze a structural element, you must first find out these things and then accordingly choose the theory. I will explain number of theories are available for different kind of thickness and ratios. So, under that plane stress assumption, the constitutive relations. I would like to say strain and stress relations. We have assumed that sigma zz is 0, tau yz is 0, tau zx is 0. So, you will get only non-zero components sigma xx, sigma yy, tau xy and their compliance coefficients. So, this is the, I would like to say that reduced strain stress relations for the plane stress case. Now, if you want to invert it, inverting it gives stress strain relations. So, where it is represented by Q11, Q12, Q12, Q22, Q66. So, stress strain relations for the case of plane strain case is reduced to like this, where Q11, Q12, Q22 are nothing but, sometimes I would like to say Ij, where I goes from 1, 2 and 6 and J is also goes from 1, 2 and 6. They are known as reduced stiffness matrix or reduced stiffness. Then what are these in terms of compliances? You can see if you are inverting a 3 by 3 matrix S11, S12, 0, 0, S12, S22, 0, 0, 0, S66. If you are inverting that matrix, let us say any matrix S hat, so invert. So, in that it will have those components S22 by S11, S22 minus and S1223. These are in terms of compliances. As I have told you that engineering constants, we are more familiar with that, like Young's modulus, Poisson's ratio. Generally, we are able to calculate the mechanical property in terms of engineering constants, because we have a UTM, there we can directly find out the Young's modulus E1, and similarly we can find out the Poisson's ratio or shear modulus. So, in terms of that, one can see that if it is a orthotropic material, it will be Ex Young's modulus along x direction 1 minus mu xy and mu yx. So, the Poisson ratio mu xy not equal to mu yx for orthotropic material. This is very important thing, and if you want to write in terms of number 1, number 2, number 3 index form, so E1 1 minus mu 1 to mu 2 1, which is equivalent, you can say that C11. Similarly, Q12, Q22, Q66, Q12 is a C12, there E2 1 minus me, this denominator remains constant, you can remember that thing. See, Q12 means mu12 and E2, say Q22 means E2, Q66 is nothing but Gxy or G12 C66. For the case of isotropic body, that mu12 is equal to mu21, then this relation reduced to E by 1 minus mu square. So, most of the time when you going to develop a plate governing equation for a isotropic plate, then you need to just E 1 minus mu square. So, you can obtain that Q11. Similarly, Q22 will also same, and Q12 will be mu times of E 1 minus mu square, and these standard set of relations are given in the book. You can go through a K. Chandrasekhar book or K. Bhaskara book, both things are given. You have to just be aware, okay, these kind of things are available. You need not to remember that what is Q11, what is the expression of this. Just you must know, okay, there are something that like Q11 and Q22, and they are the reduced stiffness matrices, and their elements looks like that. So, for when we are going to apply a plane stress assumption, then we have to use Q11, Q22 instead of normal stiffness matrix. Now, a concept of plane strain and its application. Plane stress, I have told you that thickness is very small. What is the concept of plane strain when you are going to analyze? Let us say there is a bridge or there is LPG storage tanker. I would like to it here. LPG storage tank, or you say that oil storage tank. You will feel that whatever the radius, and this length may be up to 70 meter, and this may be up to 2 meter or 3 meter, or you are talking about a bridge, civil engineering structures, let us say in that bridge width, and this length goes up to 2 kilometer. This may be around 200 meter, not more than that, even 100 meter maybe, and this length may be 200 kilometer. Or if in the big cities you see this metro flyovers, like specifically in Delhi or in Bombay or in Kolkata, the flyovers over which metros is running. So, they can also be analyzed under the case of plane strain. So, one major thing you have observed that if one direction length is infinity, okay, and this too, this is your thickness direction and this is your length direction, then we treat as a plane strain case. You may question that it can be treated as a beam, but the condition of a beam is that this length A nearly or equal to the maximum 5 times of h, not more than that. But if A is bigger than that, for the case of thickness, let us say it may be 10 times, you go for that, let us say 1 meter and it may, 1 and it may be 0.1. So, 10 ratio of 10, then you cannot treat this structural element as a beam element. Then you have to say it is as a plane strain element. Now, you have got the concept. When plane strain element, the width is considerable, more than the thickness, at least 10 times the thickness, then you have to treat as a plane strain element. If your thickness and width is equal to 2 or maximum up to 5, then you can treat as a beam, and that comes under the plane stress case, but it is a plane strain case. Similarly, a cylinder which is very long, here also the coordinate system plays a major role in which you took the direction. So, in some of the olden book, when we talk about a plane strain case, they said that, or you say that at the flat panel, that this axis is x, this axis is y and z is infinity along the z direction. Then we say that under the case of plane strain, epsilon zz, gamma zx and gamma yz will be 0. It is saying that for an infinitely long cylinder or a flat body, if body forces and tractions are independent of that long coordinate, then the body is said to be under plane strain state. So, if I took this as my y axis, in the case of plate, if you just want to resemblance, that z is my thickness, x is my longitudinal and let us say y might be length, and it is very long. So, in that case, for the, if you want to apply that plane strain assumption, so what components of the strain will be 0? Epsilon yy, gamma yx and gamma yz, they has to be 0 if y tends to infinity, which I have written here. Now, I am coming to, I have told you that what is the plate, what is the beam, what is the shell, what is the plane stress assumption, what is the plane strain assumption. Now we have a number of models to analyze those plate problems. So we can categorize those theories into some basic classification code, that let us say u displacement along x axis, v displacement along y axis, w displacement along z axis. So very first way is that equivalent single layer, equivalent single layer theories. Under that head, it means that we are analyzing, let us say, a plate and it's a single layer. जैसे आपकी आइसोट्रोपिक प्लेट है मेड ऑफ स्टील और ए टेबल टॉप मेड ऑफ wooden, it may be steel, just as if one layer. But if we talk about a composite, it may be multi-layer case of thing. So here we can also apply these theories to analyze the composite plates or laminated plates, but assumption remains same, that it treated as a plate as a single layer. Okay. So under that classification, first is the thin plate theory, or sometimes we called classical plate theory or Kirchhoff's plate theory. Okay. And these are the two-dimensional plate theories and based on plane stress assumption. Their results valid holds when length to thickness ratio is greater than 20. Suppose you develop a plate theory and get the result solving by equation of motion, then you want to compare with the experimental results or the real analysis, then it will hold good when A to H is greater than or equal to 20. Under this head, there are theories apply for isotropic case, isotropic plates, where both small deformation considering as well as the large deformation consideration. Similarly, thin plate theory is also developed for the anisotropic material, which I am saying that for, let us say, my plate is made of composite or my plate is made of some different advanced materials, which is anisotropic or orthotropic or transversely isotropic. We can develop the thin plate theory under that assumption if the thickness is small compared to the length and width. So there may be small or large deformation, both cases theories were developed. In these theories, basically that assumptions hold that no stretching along the thickness. And no rotation of the plane, ट्रांसवर्स एक्सिस बोल सकते हैं, आफ्टर डिफॉर्मेशन. So basically in these theories, the shear stresses or the normal shear, I must talk about the shear strain, not the shear stresses. Shear strain and normal shear strains are neglected. If you go to the under plane stress case, sigma z is 0, okay, but it does not mean epsilon z is 0, it is not. But when we are going for a thin plate theory, specifically classical plate theory, there we are saying epsilon z is also 0. If tau yz is 0, it means gamma yz is 0, tau zx is 0, gamma zx is 0. They comes from there, but this extra assumption. Next, moderately thick plate theories. Here we assume that, let us say, thickness is playing a role and there is a deformation, that there it can resist the shear stresses or the transverse stresses. So, that is why moderately thick plate theories are also known as shear deformation theories, and they are also two dimensional theories. They may be categorized like first order shear deformation theories and higher order shear deformation theories. In higher order, generally we take odd terms like third order, fifth order, seventh order. I will explain later on why we are considering only third order, fifth order, not second order and fourth order. So, first order theories further isotropic and anisotropic, higher order isotropic and anisotropic. So, I would like to emphasize here that let us say first order theory was developed for a isotropic plate later on in 1960s or 70s. Now, you have material is changed, your material is piezoelectric or your material is functionally graded, which is an isotropic material, or some other material, advanced ceramic, or you have included something else, layer wise composite. Then the same theory can be used to analyze then anisotropic plate. People have developed their results for using the first order assumptions. It has been found that first order theory gives slightly less accurate results and they require some shear correction factor for properly or accurately describing the shear stresses. But when we go for the higher order theories like the very famous theory TOT or Reddy's third order theory. So, they do not require the shear correction factor, and even these theories can predict the thick plate behavior very accurately. They are basically good for isotropic. When you go for anisotropic material, one can develop third order theory for an anisotropic plate, but their behavior may not be predicted very well, because when you have a layer concept, so something extra element you require. Then thick plate theories, when your thickness is not negligible, then you have to go for thick plate theory. So, that theories are generally based on theory of elasticity and these are three dimensional in nature. I would like to say that most accurate here I would put that more accurate, not most, and classical may be just accurate. If you want to understand the mechanics or really very accurate estimation of the stresses or the strains or the different boundary effects, then three dimensional theories is required. Whether the thickness is small or big, they can capture both the effects. But for these theories, you have to be in that range. So, for this case, S must be greater than, I would like to say 6 or 5 and less than 20. So, in that range, higher order theories accurate more good results, and this basically when you have S4, 5, 2, 3 whatever, they can give you exact solutions. Now, a concept, when the plate is made of a isotropic material, there is no layer wise concept, then you do the analysis by using whether third order or higher order or classical. If it is in that range, accurately predict the behavior. But when you have a concept of anisotropic material, then those equivalent single layer theories produces inaccurate results, not completely far but slightly inaccurate results. So, to overcome those limitations, researchers developed that layer wise plate theories or discrete plate theories. Here, in plane displacement fields is approximately layer wise, or whereas W is usually assumed to be independent of Z. Like if you have these layers, let us say 2 layers, so here to here you will have some variation, let us say U1, and here to here you will have U2. So, each layer will have displacement field. Previously it was having same thickness, only one variation. So, you see that as the number of layer increases, number of variable increases, so computational cost increases. The disadvantage of this theory, though it can predict the results very accurately, and practically the composite laminate or you call a composite plate are made of at least 100 layers or 90 layers, very thin layers, sometimes it may be 50, but if that theory is applied, you will see that number of unknowns will increase too much. Then the equivalent single layer theories, as I told it, in a single layer plate, displacement field assumed to have a global function dependence. Then the researchers are come up, okay, equivalent single layer theories are not giving good results, and layer wise theories having that if you increase the layers, number of variables increase, so number of differential equations you have to solve. So, these days now if you talk about now, okay, we have a very good storage space, big computers, we can even go for layer wise, no problem, good results. But it is in 1970s or 1980s or 1990s when we do not have that much of high capacity of computers. Then we talk about, okay, some theories which can give lesser, which have some lesser unknowns. So, a concept come that efficient layer wise theories, or sometimes we call this refined theories. So, in these layer wise theories, these are layer wise theories in which number of primary displacement variables is reduced to that of a corresponding ESL theories. It's a major concept. By enforcing the shear traction free conditions at the top and the bottom and the condition of continuity of transverse shear stresses at the layer interfaces. What is the meaning of this? Let us say, if you have a plate, and just I am giving an example of two layer, it is saying that at the top and the bottom there are no shear stresses, only top and bottom, and at this interface. For a perfect bonding case, because materials are perfect, if it is not perfect bonded, it may slip, so it will not provide the required function. So, for the perfect bonding, whatever the u, though it is a layer wise variation, whatever u will get from, let us say, at this u at this interface from the bottom approach, and then you go for u2 from the top approach. So, at this interface they should match. If you have gone through a finite element analysis, or you have sometimes developed a solution in any abacus or ANSYS, then there you will also that in the elements, that at the junction of that they should match, if you get from there or there. Their variation is away from there, but at this junction for a perfect bonding case, so that is the why it is known as continuity of transverse shear stresses. So, there they are saying that tau yz and tau zx, basically transverse, and sigma z has to be continuous over the surface, as well as displacements later on. Otherwise, there will be slipping of the plate if this continuity is not maintained. So, people have done the analysis imperfect bonding. There you can assume that whatever you are getting from u, there is a sudden jump, or whatever shear stress you are getting from the bottom and the top plate, it may have different. So, in real scenario, yes, but theory becomes more complicated, that this theory will not be able, then we have to consider imperfect bonding. So, it will have some more complex cases, but it will be near to the real picture. In actually there is slight motion may take place. You cannot like if I talk a concept of engineering mechanics, that a perfectly rigid body. So, it is just a hypothesis that a body cannot deform, but it if you apply a pressure, it may deform into slightly that pinch. So, similarly here, there may be some imperfection there. So, So, that can be taken care, but that theory will be slightly basic, this concept will change. So, I am talking about this layer wise theory where we say that condition of continuity of shear stresses and top and bottom free. So, one of the theory which is developed by Professor Kapuria for the piezoelectric plate, zigzag theory. For elastic plate it was developed by Amcho. So, these theories are known as efficient layer wise theories. Now, I would like to explain that you have thin, thick, okay, you can define based on some geometric parameters, but there are classification based on the approach. So, basically 3 approaches are there. One is the displacement based approach, then second is a stress based approach, and third is the mixed approach, which is a, I would like to say, a recent concept. So, displacement based approach, you will find 90% of the plate theories are based on the displacement field assumption. Under this approach, we assume the displacement field first and then find out the stresses, strains, and then using the principle of virtual work, develop a set of governing equation and solve it. And the another case is the stress based approach. If you that stress are known or stress are assumed first, and then by integrating you can find out that from the stresses you find out the strains, and the strains you find out the displacements. So, reverse approach. So, in this first approach you do differentiation. Here you do integration. So, you are going back. So, stress you assume something, then you find out the strains using the constitutive relations, and then find out the integrating of u. So, generally in theory of elasticity we go that Adey stress functions, Lechtinsky stress functions or Casapagoglou stress functions. So, you assume those functions and try to satisfy the equation of motion and solve those stresses. Once you know the stresses, then you can find out the strains using the constitutive relations. Once you know the strains, then you can go for the displacements. Then we have a mixed approach concept. Under this mixed approach concept, we take field variable displacement as well as the stresses. So, generally if you see my research papers, there you will find we have used the mixed approach for developing a 3-dimensional solutions. The concept, why we are going to this, what is the discrepancy with that? Generally the boundary conditions, displacement based approach can give very accurate result if the boundaries are in terms of displacement. Let us say if you have a fixed beam, it means here u is 0 and w is 0 in terms of boundary conditions are in terms of displacement. And let us say again you may have fixed. There may be cases, so that displacement based approach, that displacement boundaries are satisfied exactly, but if here is free, it means displacement can be anything, but stress must has to be 0. Stress resultant if I talk about that has to be. So, at this along the thickness direction we are satisfying the stress resultant conditions, not the stresses at every point. Similarly, the moment resultant has to be 0. So, when we are interested in terms of some local effects, then these theories may not provide accurate results. Now, come to the stress based approach. The boundary condition in terms of stresses, they satisfied very nicely, but displacement boundary conditions again they have to be integrated form or some other form has to satisfy. So, mixed approach is required because if you see the cantilever beam, it is a mixed kind of boundary conditions. At the one edge all the stress components are 0, at the other edge all the displacements are 0. So, this is the mixed kind of boundary conditions. So, if we have a mixed approach in which you have a displacement as well as the stresses, so you can satisfy the boundary conditions exactly, or I would like to say in a more accurate sense. If we talk about 3D, then we say exactly. If you talk about 2D, then we say that in more accurate sense. Then displacement field assumptions. This is the very important slide. I would like to say that nobody gives you like this in a books, that how much primary variables you have for a classical FSDT or TOT. So, I am going to tell you, let us say for a classical theory, so U is assumed as like this, V is assumed like this, and W is assumed like this. So, you have a 3 primary variables, U naught, V naught, W naught. So, just by looking your displacement field assumption, I can tell you how many number of governing equation or equation of motion you will get. You will get 3 equation of motion. If you have a FSDT theory, then you have phi 1 and psi 1 and 3 this. So, 3 plus 2, there will be 5 unknowns. Then if you go to the third order, so you may take, sometimes they are not taking phi 1 as a unknown, they just replacing with this, then it will also reduce to 5. But if you go that, let us say this is also unknown and this, then it will be 7 and 7 equation of motion. So, basically you have to solve 3 simultaneous differential equations, 5 simultaneous differential equations and 7 simultaneous differential equations. So, solving simultaneous differential equation or developing a program for that is really a huge task. It is not that you are solving just a algebraic equation like a matrix, this thing. So, later on for some cases it becomes like just a linear algebra if you talk about all edges simply supported. But if you have a different as conditions or a Levy type support conditions, then you have to solve ODE, simultaneous ODE. So, their algorithms or some difficulty level are there. So, here our week 1 ends. So, I have completed the basic principles, then the basic relations and the classification of cell theory. So, next in the week 2 we will develop classical plate theory considering the von Karman nonlinearity. Thank you.